Okay, this is section 6.8, our discussion of electron configurations of elements greater than hydrogen. Okay? So the idea here is that atoms have electrons, and we can apply the principles of quantum mechanics to figure out the arrangement of those electrons around the nucleus. Knowing that electrons occupy these regions of space around the nuclei, which are called orbitals, atomic orbitals, we can use our understanding of these atomic orbitals to figure out which atomic orbitals the electrons are going to occupy within the physical limits of the atom. So let's remind ourselves that we have this thing called notation, this energy level notation, electron diagram notation, and that each atomic orbital has a certain energy. So the top figure over here shows us the relative energies of the atomic orbitals for multi-electronic atoms, so meaning any atom that's not hydrogen. If you recall, in the previous section, section 6.7, the only thing that mattered in terms of the energy of these orbitals was what the value of n was, the principal quantum number. Well, it turns out that if you have more than one electron, that rule goes out the window. It's just not true anymore. So for Pauli or multi-electron atoms, the arrangement of electrons takes on a different pattern. The 1s orbital is still the lowest energy orbital, followed by the 2s. But there's a splitting that occurs, and the 2p orbitals are now higher in energy than the 2s. And the 3p orbitals are higher in energy than the 3s. And the 3d atomic orbitals are higher than the 4s. So it starts to get kind of complicated there. So there is a notation or a mnemonic you can use to figure out the order. Starting with the lowest energy right here, with the 1s, so we would start right here. It would be 1s, and then we draw a diagonal. Then it would be the 2s, then the 2p, then the 3s, then the 3p, then the 4s, then the 3d, then 4p, 5s, 4d, 5p, 6s. So when you finish here, you go back up to the next one, back up to the next column. So 4f, 5d, 6p, 7s, then you go back again to the 5f, 6d, 7p. And that's the order of filling. The electrons go into those orbitals in that order. Okay? That's not obvious, and there are ways to develop rules for it. But essentially this diagram down here at the bottom is probably the best way to remember it. This diagram at the bottom, you can make that diagram pretty easily if you just take a look at it. All the S's are in the first column, all the P's are in the second column, then the D's, and then the F's, right? And you just draw diagonals. The numbers get larger as you move down, and then that'll give you the order, okay? Now, what happens is, because electrons are fermions, they must obey a particular law, which is called the Pauli Exclusion Principle. Pauli, named after Wolfgang Pauli, Exclusion Principle. The Pauli Exclusion Principle says that no two electrons in an atom can possess the same four quantum numbers at the same time. So for example, if you had two electrons in an atom, so I'm going to call them electron 1 and electron 2, and then you made a little table of the four quantum numbers. Let's say this is a 3, a 2, a 1, and a plus 1/2. So there's your four quantum numbers for electron 1. What the Pauli exclusion principle says is that this is impossible. You cannot have the same 4 quantum numbers for more than one electron simultaneously in the same atom. In different atoms, it doesn't matter, but if they're in the same atom, there has to be a difference. So there are many different possibilities, right? This could be minus a half, and then you're okay. That would not be a violation of the Pauli exclusion principle because one of the quantum numbers is different. Okay? Now, if you think about it, this would be called, both of those electrons, we would call that 3D, right? Because remember our notation, this is n value, and then this is L. And we're using the notation, the letter notation. So if L equals 0, that's a s orbital. If L equals 1, it's a p orbital. If L equals 2, it's a d orbital. So both of those electrons are in the same subshell. They are in the 3D subshell. Furthermore, they have the same value of m sub L. So they're actually in the same orbital. So each orbital, which we'll represent as a little box, has 3 quantum numbers associated with n, L, and m sub L. Okay? So that's an orbital. So that means these 2 electrons are in the same orbital. However, they have different spin quantum numbers. One is plus a half, the other one is minus a half. So that's why they're allowed to be in the same orbital. So the way we represent this is by using arrow notation. An arrow pointing upward. And it's up to you. You could do a half arrow or you could do a full arrow. Different books will do different notations. It just has to be pointing up. When the arrow is pointing up, that means plus a half. M sub s is plus a half. If the arrow is pointing downward, then m sub s is minus a half. Spin down, we call that. So spin up, spin down. Now, the Pauli exclusion principle says that these electrons have to have at least one difference in their quantum numbers. These 2 have different in their quantum numbers. So they're going to be in the same orbital. It's just that one will be spin up and the other one will be spin down. Okay? So that's a possible arrangement of electrons. Okay? Pauli exclusion principle. Now, there's another rule, experimental observation, which is called Hund's rule. I'm sorry, my apologies. The Aufbau principle. The Aufbau is not a person. Aufbau is German for filling up. This is called the filling up principle. And the filling up principle says the following. Electrons occupy, they have a tendency to occupy the lowest available energy orbitals. Or let me put that a different way. They have a tendency to occupy the orbitals at the lowest energy. Okay? Now, because an orbital can have 1 electron spin up and 1 electron spin down, that puts a maximum of 2 electrons per 1 orbital. Now that's actually going back the Pauli exclusion principle, because the Pauli exclusion principle says no 2 electrons can have the same 4 quantum numbers simultaneously in the same atom. If you have 2 electrons in an orbital, and one is spin up and one is spin down, they would have a difference in their m sub s value. But all the other quantum numbers would be the same, n, L, and m sub L. So that means you can have a maximum of 2 electrons in an orbital. Okay? So here's what happens according to the Aufbau principle. The lowest energy orbital is the 1s. So now I'll write the 1s outside. you can have a maximum of 2 electrons in it according to the Pauli exclusion principle. Now this orbital is full. So the next available orbital would be the next highest in energy, and that's the 2s. And again, the maximum number of electrons this orbital can have is 2, according to the Pauli exclusion principle. And one would have to be spin up, and the other one would have to be spin down. So what happens is, if you have an atom with a lot of electrons, meaning more than 2 or 3 or 4, the electrons start spreading out into these atomic orbitals, starting with the lowest energy orbital first, 1s, followed by the second available orbital, the 2s, followed by the next available orbitals. There's 3 of them, the 2p. And once each of those 2p orbitals is full, then the 3s gets filled. And then once the 3s is filled, then the 3p gets filled, and so forth and so on, filling out these atomic orbitals. So if you have, let's say, 47 electrons, 47 electrons are going to fill quite a few of these atomic orbitals, right? Because you can fit 2 into each orbital. Okay? We'll practice that, of course. The Aufbau principle. You start at the lowest energy available, the orbital at the lowest energy available, then you move on to higher and higher energy orbitals. There's also something called Hund's rule. Hund's rule says that for degenerate orbitals, meaning orbitals at the same energy. Degenerate means same energy. An example of that would be the 2p orbitals. Right? These are degenerate orbitals. They're at the same energy. For degenerate orbitals, which generally means a subshell, spin is maximized. Now, in practice, what that means is, if you have more than 1 electron, let's say you have 2, maximizing spin requires the electrons go into separate orbitals with parallel spins. These are called parallel, meaning they're pointing in the same direction. Okay? That maximizes spin. Spin is additive. So if you wanted to know what the total spin of these 2 electrons were, they're both plus a half. So you get 2 halves, right? You get 1 plus 2 halves. Imagine you did this. Imagine you said, hey, it's a 2p subshell. I'm going to do this. Would that be maximizing spin? It wouldn't, because the first one is plus a half, but the second one is minus a half, and that would be 0 for your total spin. So that minimizes spin, so that's not observed. Within degenerate orbitals, what's observed is the electrons move into different orbitals in the same subshell, right? They're degenerate. In the same orientation, meaning they're parallel spins. By the way, these would be anti-parallel. Right? Opposite directions. Okay? So this is Hund's rule. Within a subshell, within degenerate orbitals, what's observed is a maximizing of spin. Now, once you get 1 electron into each of those orbitals, if you have another electron, there's no choice. It has to pair up and be counter or anti-parallel to the first one because of the Pauli exclusion principle that if they're in the same orbital, they have to be opposite spin. So we can't violate the Pauli exclusion principle. Hund's rule just is a rule about the first electron in the orbitals. Okay? So let's talk a little bit about notation. If we have a hydrogen atom, we can represent its electron configuration in the following way. the 1s orbital, remember hydrogen only has one electron, so the 1s orbital is going to have one electron. By convention, by agreement, if we put one electron in an orbital, we point it upward, we make it spin up. Okay? That's just the convention of how we normally do this. It's an agreed upon notation. Now, this can be written in a shorthand notation as 1s1, meaning it's the 1s orbital, or the 1s subshell for that matter, and this is the number of electrons in that subshell. There's only one, right? One electron. So imagine you went up to helium. Helium has 2 electrons. So you could have one electron and then a second. That's 2. So we would write this as 1s2 because you've got 2 electrons in this orbital. Technically it's in the subshell, but it's also in the orbital. Now I'm going to move up. Let's go to carbon, for example. Carbon, and notice I'm going to draw this horizontally instead of vertically because we have a tendency to write left to right, not from bottom to top on paper. So with carbon, carbon has its atomic number 6, so it has 6 electrons. So I'm going to draw a few orbitals here. Okay, so there's 3 orbitals. So this is 2s and then this is 2p. How do I know it's that? Well, 1s, 2s, 2p, right? I'm using this diagram down here at the bottom. Okay. Why do I know it's 3 orbitals for the 2p? Well, that's shown up here at the top, right? There's 3 orbitals there. So 2p has 3 orbitals. P orbitals, there's 3 of them for a given shell. And then the d, there's 5. 6 electrons. So here's what we do. First one here, spin up. Again, convention is the first one goes spin up. There's still room for an electron in that orbital, so we put it here. Higher in energy then, Aufbau Principle. Electron 3, electron 4, right? We're going to fill the orbital, then go to the next subshell. The next subshell is higher in energy, that's the 2p. We've only got 2 more electrons to go, right? That's a total of 6, and we've already done 4. Now we use Hund's rule. Hund's rule says that if the orbitals are degenerate, spin is maximized. And the way we represent that is by showing the electrons spin up. Okay? They're both spin up. That maximizes spin. So in terms of our notation, we would write 1s2 because there's 2 electrons in the 1s subshell. 2s2 because there's 2 electrons in the 2s subshell. And then 2p2 because there's 2 electrons in the 2p subshell. So it is important to memorize the order of filling. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, so forth and so on. Okay? And then you can apply this to heavier and heavier elements. Okay? So let's try one that has more electrons. And it gets to be really fun. This is actually probably one of the funnest things that we do in general chemistry are these electron configurations. Once you get the feel for it and you start to master it, you can really impress your friends. Okay, so let's try one that has many more atoms. I'm going to try element number 10, which is neon. Now the thing about this is all you need to know is the number of electrons. Okay, so here's our, I'll do this one vertically. You can do it vertically or you can do it horizontally. The nice thing about doing it vertically is that then you can write to the right, you can write the name of the subshell. And again, even though I'm not getting the relationship in terms of how high up the energies are, it shows you we're really just trying to get the configuration, where the electrons are. Okay? Again, how did I get that order? I got it from this bottom part here. 1s, then move to 2s, then 2p, so forth and so on. 10 electrons. A maximum of 2 electrons per orbital. If you're in degenerate orbitals, meaning that you're in orbitals that are in the same subshell, more than one in the same subshell, you got to apply Hund's rule. So there's 10 electrons. So the first one in, lowest energy, spin up, then spin down. You put the one up and then down. Maximum 2 electrons per orbital. Go to the next orbital. Spin up, spin down. Now we're up to 4. Hund's rule, 5, 6, 7, right? Those 2p orbitals are all at the same energy. They're degenerate orbitals. So that means we got to spread out to maximize the spin up. We've now done 7, 8, 9, and 10. There's our 10 electrons. How about that? We can write this in a shorthand notation. 1s2, 2s2, 2p6. How about that? All right, so there's one. Let's try another one. We could try one that actually has more electrons than that. Let's try one that has a lot more electrons than that. Let's try bromine. Bromine has 35 electrons, right? Just as a reminder, in the periodic table, the atomic number of bromine is 35, which is really the number of protons in the nucleus. But since it's an atom, the number of electrons is the same as also 35. Okay? So now we got 35 electrons to go. So I'm going to start way down here and do 1s, and then 2s. Oops, what happened there? 2p. 3s. 3p. 4s. 3d. 4p. I think that's enough right there. I don't know for a fact, but I'm pretty sure, just based on thinking about this. Bromine is in the 4th row, so it probably goes up to 4p. It's a non-metal. Okay, so 35. Again, the order, how did I get that order? Down here, that's where I figured it out. We start at 1s, just move to the left, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, so forth and so on. Okay, 35. Maximum of 2 electrons per orbital. That's the Pauli exclusion principle. Hund's rule says you maximize spin within a subshell. That's a subshell. 2p is a subshell. But since we got to go all the way up to 35, it's going to be completely filled. In fact, I'm not even counting yet. I'm just going forth and filling these out because I know I've got 35 electrons to go. So see, 3D, I'm going to do this as well. The P's and the D's, you want to do Hund's rule. It's not an issue for the S because there's only one orbital in a subshell for the S. Okay, so far that's 30. So we got 5 to go. 1, 2, 3, Hund's rule, 4, 5. And there you go, we got it. That's the configuration. Let's do the shorthand notation. 1s2, okay, there's 2 in there. 2s2, there's 2 in there. There's 6 over here. 2 here. 6 here. 2 here. 10 here. And then 5 here. And there you go. There's your electron configuration as a shorthand notation for the bromine. Now, one thing that comes up is counting unpaired electrons. Sometimes we're asked to do that. If you want to count the number of unpaired electrons, all you do is you note that if you have 2 electrons in the same orbital, their spins counter each other. They cancel each other, essentially. So there's only 1 electron that's unpaired. So for that particular element, there's 1 unpaired electron in the bromine atom. Okay? So you want to practice as many of these as you can. It's sort of like naming compounds or balancing equations. practice as many of these as you can.